In chapter 14, we apply what we've learned about equilibria to acid-base reactions. We're going to begin with defining what we mean by an acid or a base and how acids and bases react with one another. And then we're going to work through a series of quantitative calculations that are concerned with acid-base equilibria. This is a very long chapter. It's considerably longer than some of the other ones, and we'll probably spend 2 or 3 weeks on this chapter. So we've previously talked about acids and bases in Chemistry 161 and about the reactions of acids and bases. And the important thing to remember is that acid-base reactions are proton transfer reactions. So just like redox reactions are electron transfer reactions, and we can recognize that a reaction is a redox reaction because there's a transfer of electrons, when we're thinking about acids and bases, we should always be thinking about how protons are moving. So in Chemistry 161, we defined an acid as a substance that has hydrogen in its formula and when dissolved in water ionizes to form what are referred to as hydronium ions, H3O plus AQ. So a classic acid of this type is hydrochloric acid. So if you take hydrogen chloride, which is a gas, and you bubble that through some water, what you'll form is chloride ion and hydronium ion. So it's clearly an acid. So this definition of an acid that relies upon the formation of hydronium ion when the substance is dissolved in water is called the Arrhenius acid definition. And we've already seen some Arrhenius acids in the lab and elsewhere, and typical examples would be things like hydrochloric acid, nitric acid, and sulfuric acid. There's another definition of an acid, and that is in terms of how it behaves with respect to hydrogen ion. So an alternative definition of an acid is a substance that donates hydrogen ions. So what's happening when that hydrogen chloride is dissolved in water is the hydrogen chloride is donating a hydrogen ion to the water molecule, and that leaves behind a chloride anion and forms a hydronium ion. And this definition, where we define the acid in terms of its proton transfer identity, is called the Bronsted-Lowry definition of an acid. And it's great. It's as good as the Arrhenius acid definition, and in fact better, because it doesn't have to rely on the fact that the substance is dissolved in water. All Arrhenius acids automatically become Bronsted-Lowry acids. In the case of an Arrhenius acid, all that's happening is your hydrogen ion is always being donated to water, but the Bronsted-Lowry definition, it doesn't require the presence of water. In the Bronsted-Lowry model, we can also define a base, and a base in this model is just said to be a substance that accepts hydrogen ions. So in this case, the hydrogen ions are moving from our hydrogen chloride to our water. So what that means is the hydrogen chloride is the acid and our water is the base. So when an acid ionizes in water, it's the water that is functioning as a base. It is being the proton acceptor. So it's interesting to talk about strong acids and weak acids. We're going to talk about strong acids first of all, but strong acids are all covalent compounds. That is, that they are molecular in their nature, that when they are dissolved in water, they completely 100% ionize. So that means that 100% of their protons get transferred to water. That is, once the substance is dissolved in water, there are no more intact acid molecules that remain. So that's a characteristic of a strong acid. It's a highly effective proton donor. So there are 2 common classes of strong acids, and we saw some of those in the previous table. There are ones that are called binary acids. They're also sometimes referred to as hydrohalic acids, and these are the 3: hydrochloric acid, hydrobromic acid, and hydroiodic acid. So they all involve hydrogen bound to a halogen. That's why they're called hydrohalic acids sometimes. It's important to recognize that hydrogen fluoride is not a strong acid. The other class of strong acids are things that we call oxoacids, but a special class of oxoacids. These are oxygen-containing acids where the number of oxygen atoms is at least 2 more than the number of hydrogen atoms. So a good example here is sulfuric acid. So we've got 2 hydrogens, but we've got 4 oxygens, you see? So we've got 2 more oxygens than hydrogens, so that makes it strong. Then we've got nitric acid, HNO3. We've got 1 hydrogen, and then we've got 3 oxygens. So again, we've got 2 more oxygens than hydrogens. Or perchloric acid, HClO4, where we've got 4 oxygens and only the 1 hydrogen, so we've got 3 more oxygens than hydrogens. So as long as you've got 2 or more oxygens than hydrogens, it's going to be strong. So you need to be able to tell from the formula of an oxoacid whether it is strong or not. For the binary acids, all you really can do is memorize these 3. So, a strong acid is defined as a covalent compound that ionizes 100% when dissolved in water. And the question is why do they do that? Why does hydrogen chloride transfer its proton to water? How come it just loses this guy and gives it up to the water? Why does that happen? And it doesn't just do it a little bit, it does it 100% because it's a strong acid. Well, the reason is it's all about how the electrons are shared in our water molecule and in our acid molecule. So when we have a covalent compound like water that contains 2 or more types of atoms that are different, the electrons are going to be shared unequally. So hydrogen's way over here, it's the non-metal that's kind of the least electronegative, and oxygen is way over here. So oxygen has a far greater electronegativity than hydrogen. And the net result of that is we end up with a negative end of a water molecule and a positive end because the oxygen is far more electronegative than hydrogen. Now when we have something like the strong acid HCl, we have a similar effect. This bond is very, very polar and the electrons are way over on the chlorine net. So again, that end is going to be very negative and that end is going to be very positive. So how does this help explain the behavior? So water molecules are strongly polar. The oxygen end is negative, the hydrogen end is positive. And as we know, because of this dipole, water molecules stick to one another. They have what we call intermolecular forces. In fact, it's a special kind of dipole-dipole interaction called the hydrogen bond. If we consider an acid like HCl, it will also be polar. Now, this is going to be very polar because there's such a big difference in electronegativity between these 2 atoms. Hydrogen often forms very polar bonds because it has such low electronegativity for a non-metal. It's going to form particularly polar bonds when it's bonded to highly electronegative elements. Good examples would be oxygen, chlorine, bromine, iodine. These bonds are going to be really polar. Because the bond is so polar, the hydrogen atom barely gets any share of the electrons at all and is only weakly held to the atom that it's attached to. That is, the bond holding the hydrogen atom in a strong acid is fairly weak. Now, it's also worth recognizing because water molecules are strongly polar, because strong acid molecules are fairly polar, the attraction between a strong acid molecule and a water molecule will be very strong. And what happens is that a covalent bond will readily form between the oxygen on our water and the hydrogen on our acid. So what happens, here's my HCl molecule approaching my H2O molecule. We've got the HCl molecule is going to come in with its positive end first towards the negative end of the water molecule, which we know has 2 lone pairs on it. And so what's going to happen, these lone pairs become shared with the hydrogen atom, and the shared electrons, which were much closer to the chlorine than they were to the hydrogen, they just kind of move in even closer to the chlorine, and that bond breaks. So the net result is that we form a chloride anion, and we form a covalent bond to the hydrogen atom, and we form a hydronium cation. So what do we have? We have proton transfer. In this way, the proton moves from the HCl to the water. Now, it's important to realize that the hydronium ion will be hydrated, so it'll be surrounded, this positive cation, by a large number of water molecules, all with their negative ends pointing in. So we don't have, free protons or free hydronium ions really floating around in aqueous solution. We always have what we call hydrated hydronium ions. We never have just plain old hydrated protons, even though we might talk like that. So it's important to recognize that we frequently will write H plus in AQ instead of hydronium ion, because they kind of do mean the same thing, and we get to save a couple of characters. So let me just see, if I just have an H plus, as soon as I combine it in water, it's going to make a hydronium AQ, but a lot of people will just save time and will just write H plus AQ, and that's okay. You just kind of have to understand it. So sometimes this causes an issue. Instead of writing, when you look at answers to problems on the internet and stuff, you want to be very careful whether they really are fussy about this, and whether they want H plus, or whether they're happy, whether they really want H3O plus, or whether they're happy for you to put H plus. All right, so let's have a look at this acid dissociation reaction. We've got an acid here interacting with water, and it's going to transfer a proton. It forms the hydronium ion and an anion. And we could write an equilibrium constant for this reaction. We're going to call that equilibrium constant Ka, because it's for an acid. So it's going to be our product concentrations over our reactant concentrations. But because the water is a liquid, we're going to leave that out of our expression. So this expression that we see here for Ka, it's the equilibrium constant for the ionization of an acid. Sometimes people will call it an ionization constant. Other times people will call it the acid dissociation constant, but this expression for Ka is going to be the same for all acids. Now, if you have a very strong acid, the Ka expression will be a lot bigger than 1, like 10 to the 5, or even 10 to the 10 is not uncommon. And typically people won't write the equilibrium constant. But if you have a Ka that's sort of, less than 10 to the minus 1, then people do tend to write the arrows for the, instead of the equilibrium arrows, to indicate that it really is a true equilibrium. Okay, so weak acids tend to have Kas significantly less than 1, and most of the acid molecules are in the undissociated form. So we don't really see that many weak acids in the lab. We don't use them very often, with perhaps one notable exception. But common weak acids are hydrofluoric acid, and then other acids that don't involve oxygen. So hydrocyanic acid is another example, H2S. So acids that don't involve oxygen and haven't already been labeled as strong are also weak. Oxo acids where you don't have enough oxygens. right? So where you don't meet that 2 or more oxygens and hydrogens criteria. So here's a good example. Here it's nitrous acid. You only have 1 more oxygen than hydrogen. Okay, so oxo acids, where you just don't have enough oxygens, are weak. And then we've got carboxylic acids, and the classic example is acetic acid, and they all kind of have this grouping of atoms COOH at the end, and you'll learn later in organic chemistry exactly what's going on with this group of atoms. These are a very interesting class of compounds, but all carboxylic acids are weak. So if you're given the formula of an acid, you should be able to categorize it as being either weak or strong. Your strong acids are HCl, HBr, and HI, and then those oxo acids where you have 2 or more oxygens than hydrogens. When we write their expression for their ionization reaction, we're just going to use a forward-directed arrow, not the equilibrium arrow. The weak acids are acids that are hydrofluoric acids, and then other acids that don't contain oxygen. So I gave the example HCN, H2S. Oxo acids, where you have you don't have enough oxygen, so the number of oxygen atoms is less than 2, greater than the number of hydrogen atoms. And then this special class of carboxylic acids, which have formulas that end in the COOH. Very common example we're going to be looking at a lot is acetic acid, and that's the acidic component that's actually found in vinegar. So Ka values all have this expression and can be written for an acid, whether it be weak or strong. It's not particularly interesting for a strong acid most of the time. So they're all of this form. There's a whole bunch of them in the appendix of your textbook. Probably the one that you probably will commit this to memory. Acetic acid, we use it all the time. 1.76 by 10 to the minus 5 is the Ka there. You can see the Kas are all very small, indicating that the equilibrium favors the left-hand side. That is the molecular form rather than the ionic form. Formic acid, also a carboxylic acid. You can see that there. Ends in COOH. This is it's the acidic component in ant bites that causes the sting. Hydrofluoric acid, we already mentioned, that's the only hydrohalic acid that is weak. Not quite as weak as acetic acid, 10 to the minus 4 there on the Ka. Hypochlorous acid and nitrous acid are examples of oxo acids, where we have equal numbers of oxygens and hydrogens, or in this case, we only have 1 more oxygen than hydrogen. So they aren't going to be strong because they just don't have enough oxygens. You can see hypochlorous acid is our weakest one that we've got here, Ka 10 to the minus 8. So really, very, very weak. Okay, there's a big table of those in the back of the book. That's where you're going to look if you need a Ka. Now, when a weak acid like HNO2 dissociates in water, what happens? It transfers a proton over to the water, right? The proton donor is the acid. The proton acceptor is the base. The products, the hydronium ion and nitrite anion. Now, what's happening in the reverse reaction? Well, the hydronium ion donates a proton to the nitrite anion. So this guy is the acid and this guy is the base. So what we see is we have an acid and a base, and the only difference between them is 1 proton, right? So we have a pair of substances there where we have an acid, and then we put a proton on it and we get the base. All right, that would be an example there. So what would be, this would be our acid. Let's make that, we have an acid and then we have a base. So this would be our acid, our HA, and then this guy is going to be our A minus, our base. And you can see that the only difference between this acid and the base is 1 proton. And then we have another one over here. This is an acid too, right? And then this is a base as well. So we've got an acid-base pair, and then the only difference between them is 1 proton. See? So here's our HA, and here's our A minus. Okay, so we get these pairs like this, where we have an acid and a base, and the only difference between them is 1 proton. Okay, so we call these conjugate acid-base pairs. Conjugate acid-base pairs. And what they are an acid and a base, and the only difference between them is 1 proton. Okay, so our acid transfers a proton, forms a base, and the hydronium ion. That's the forward reaction. In the reverse reaction, our hydronium ion transfers a proton, it's the proton donor, to our conjugate base. That's the base, and that forms our acid and water. So putting some real symbols in so we can see what's going on, and also fixing our spelling mistake here. Here's our acid, you can call that HA if you want, donates a proton to our base. Acids are proton donors, bases are protons acceptors. That's our forward reaction. What does it form? It forms the hydronium ion and the nitrite anion. In the reverse reaction, the conjugate acid that was formed, the hydronium ion, donates a proton to our conjugate base, the nitrite anion, and then this guy it's functioning as a proton acceptor at this point, and then that generates our acid. So we have an acid and a base, and the only difference between them is 1 proton. And you can see that the acid always has the extra proton. And then in the reverse, it's the same, right? Here's our acid, here's our base. The only difference is that the acid has an extra proton. So we're going to be talking about conjugate acid-base pairs, things that differ by 1 proton, and the thing that has the extra proton is an acid, and the thing that has 1 less proton is a base. So, in Bronsted-Lowry acid-base theory, an acid-base reaction occurs between 2 acid-base conjugate pairs. Acid 1 donates a proton to base 2. This forms acid 2 and base 1, and then acid 2 donates a proton to base 1 in the reverse reaction. Acid 1 and base 1 are 1 acid-base conjugate pair. Acid 1 is exactly the same as base 1, but it has an extra proton. Acid 2 and base 2 are the other conjugate acid-base pair. The only difference between these two species is this guy has an extra proton and this guy has 1 less. And that's it. So here's a good example. Hydrocyanic acid, that's a weak acid, donating a proton to ammonia. What does it form? It forms the ammonium ion and the cyanide ion. The ammonium ion is the conjugate acid of ammonia. The cyanide anion is the conjugate base of hydrocyanic acid. So these are 1 conjugate acid-base pair, an acid and base that differ by 1 proton, and then these guys are another conjugate acid-base pair. You can see that the acid always has 1 extra proton than the base. Otherwise, they're the same. So, let's have a look at this one. We've got ammonia reacting with water to form the ammonium ion and the hydroxide ion. So we can see that water donates a proton to the ammonia. It's the acid. That's what's happening in the forward reaction. In the reverse reaction, the ammonium ion is donating a proton to the hydroxide ion to form the water and the ammonia molecule. So if we look at what are the acid-base conjugate pairs, it's going to be NH4 plus. This guy is the acid, and then that's the base. And then for the other pair, it's going to be water and hydroxide ion. So water is going to be the acid, and then hydroxide ion is the base. So we say this is the acid, this is its conjugate base, and then we say this is the base, this is the conjugate acid. So the conjugate is the one over here, and then over here we just label it as acid or base. All right, so the conjugate acid or base is always on the product side. Okay, and that's really it. Typically when people write them out, they'll write it acid/base as the shorthand. The generic for that might be HA, A minus, when they're just trying to illustrate what's happening. Okay, so before we wrote Ka for describing the equilibria for when an acid dissolves in water, we can also write Kb, which is the ionization constant for when a base dissolves in water, the equilibrium constant for when a base is dissolved in water. So what happens when a base is dissolved in water? The water functions as an acid, donates a proton to the base. This forms a cation, which will be the conjugate acid of our base, and a hydroxide ion, which is the conjugate base of our acid. So, writing the equilibrium constant for this process, it's our products over our reactants, but we don't have to worry about the water because it's a liquid. So it's our cation concentration multiplied by our hydroxide ion concentration divided by the concentration of our base. And similar to acids, weak bases are going to have really small kb's, much less than 1. Strong bases have much bigger kb's. We probably, if the kb is a lot bigger than 1, like say 10 to the 3 or more, then we tend not to write the equilibrium arrows, but put just a forward right pointing arrow. Okay, so what are your strong bases? They tend to be your soluble metal hydroxides, and these are most metal hydroxides except for those in group 1 and some in group 2 tend to be insoluble. So your common strong bases tend to be soluble metal hydroxides. How do they function? Well, they're ionic compounds, so they dissociate 100% to form hydroxide ions when they're dissolved in water. Sometimes you get 1 hydroxide, sometimes you get 2, depending whether you've got a group 1 or a group 2 cation. What happens when they're dissolved in water? Well, what they are extremely good proton acceptors. They will accept a proton from, say, the hydronium ion or any other acid and form water. Now, all of these strong bases, like I said, have kb's that are really big. Generally, we'll just put a forward pointing arrow if the kb is a lot bigger than 1. By that I mean like greater than about, say, 10 to the 3, rather than use an equilibrium arrow. Okay, what are your weak bases? Your typical weak bases are nitrogen-containing covalent compounds. Yeah, they all have kb's much less than 1, so ammonia is the classic, which interestingly, the kb for ammonia, which is our most commonly looked at weak base, is exactly the same as the Ka for acetic acid, which is our most commonly studied weak acid. So that kind of makes it easy to remember the value, 1.76 by 10 to the minus 5. So again, these tend to be nitrogen-containing compounds that are referred to as amines, that are these weak bases. And you can see, some of them are very weak, 10 to the minus 10, 10 to minus 9 there for the equilibrium constant. Okay. there's a whole bunch of these in the back of the book in the appendix as well. Right, so here's where it gets fun. We've seen some examples where water functions as a base. For example, if I take the weak acid nitrous acid dissolved in water, the water clearly is functioning as a proton acceptor. That makes it a base, right? It's accepting the proton. But if I take the weak base ammonia dissolved in water, then the water will function as an acid. It'll be a proton donor. So what is it? Is water an acid or is water a base? Turns out it's both, right? It depends what it's being combined with. We put these two things together, and there's a tug of war for the proton, and the one that is the stronger base gets it, right? So there are compounds like water that have the capacity to function as both acids and bases. So things that can do both, that function as an acid or base depending on what they're combined with, are described as being amphiprotic. So, yeah, that's kind of an interesting sort of concept. So that's one thing that we need to recognize, is that under some circumstances a substance might be an acid, under others it might be a base. The next thing we want to look at is how the strength of a conjugate base is related to the acid that it's derived from. So if I take something like a strong acid such as hydrogen chloride, it acts as a proton donor because it's an acid, and 100% of these molecules will donate their protons. That's why it's a strong acid. So what that tells me is that the reverse reaction, where the hydronium ion is functioning as an acid and the chloride ion is functioning as a base, doesn't happen, right? What it's telling me is that the chloride anion is ridiculously weak, right? So strong acids have weak conjugate bases. And in this case, the reverse reaction doesn't happen at all, which means that the chloride ion isn't a base at all. It's so weak that it's like non-existent, that reverse reaction. So that's a general result. The conjugate bases of strong acids are very, very weak. So the anions that are derived from strong acids, they're not bases, right? So here are a bunch of strong acids. The anions that come from them, they're very, very weak bases. Now, there's a little thing, we only ever characterize acids as being strong or weak. Are some stronger or weaker than others? Well, once you get to the point where you've reached 100% ionization, all strong acids become equally strong. So that's called the leveling effect. You know, it either does ionize 100% or it doesn't. So the classification of strong versus weak is it's either one thing or the other, and that's described as the leveling effect. So hydrochloric acid and nitric acid, they're both characterized as strong. They both ionize 100% in water. It doesn't really make any sense to characterize them beyond that. Now, weak acids ionize partially in aqueous solution. And so what that means is that the conjugate base of a weak acid is a pretty decent base. Right? It's actually a pretty decent base. So this is, again, is a general result, and it is the weaker the acid, the stronger the conjugate base. So here's a whole bunch of acids listed in order of increasing acid strength from the bottom to the top. So we see some kind of some sort of, well, these are all weak acids, so there's nothing really particularly familiar here. And what you want to recognize is that the conjugate base strength increases in the opposite direction. So the weaker the acid, the stronger the conjugate base. So things like carbonate anion are actually fairly acidic, fairly basic. So that's kind of interesting. You see ammonia in here. Ammonia is a full-blown weak base. So that's interesting. So as the acid strength goes up, the conjugate base strength goes down. Okay, now strong bases ionize completely in water. So if we think of something like sodium hydroxide, it just separates 100% to give us hydroxide ions and sodium ions. What does that tell you? It tells you that Na plus is a terrible acid. This reverse reaction doesn't occur at all. But what we also want to recognize is that all strong bases are equally strong because they all 100%. You can't do better than 100%. Again, this is another example of the leveling effect.